Hello everyone. So my task for today is to give you a review about descriptive statistics. So I am Jethro Noel True Daniels, DM Man RN. Let me read first to you the learning objectives for our topic for this week. First, to provide a quick review on descriptive statistics. Second, to have a better understanding on how to interpret data gathered from a research study. Third, to know more what is inferential statistics and how it is being used in research. And lastly, to equip learners better understanding of the data interpretation using appropriate statistical techniques. Without statistics, quantitative data would be a chaotic mass of numbers. Statistical procedures enable researchers to organize, interpret, and even communicate numeric information. So statistics are either descriptive or inferential. So we will be discussing each, or we will be having a quick review of the two, either descriptive and or inferential, since this topic was discussed to you last semester. So furthermore, descriptive statistics are used to synthesize and describe data. Averages and percentages are example of descriptive statistics. So when such indexes are calculated on data from a population, they are called now as the parameters. So a descriptive index from a sample is a statistic. So most scientific questions are about parameters. So researchers calculate statistics to estimate them and use inferential statistics to make inferences about the population. A set of data can be described in terms of three characteristics. It could be the shape of the distribution of values, the central tendency, and even the variability. So these things will be discussed further. So when we talk about central tendency and variability, they are dealt with in the subsequent sections. So let's have a quick review with this example. We have table 15.1 titled Patients' Anxiety Scores. So for our frequency distribution, so the data that are not analyzed or organized are really overwhelming. So it is not even possible to discern general trends in the data without some structure. So you consider the 60 numbers in the table provided. Let us assume that these numbers are the scores of 60 preoperative patients on a 6-item measure of anxiety, scores that are on an interval scale. So visual inspection of the numbers in this table provides little insight on patients' anxiety. Frequency distributions are a method of imposing order on numeric data. A frequency distribution is a systematic arrangement of numeric values from the lowest to the highest. Take note, it is a systematic arrangement of numeric values. So we encourage you as you pursue, as you continue with your research too, as you present the data gathered, it should be arranged systematically from the lowest to the highest, together with a count or a percentage of the number of times each value was obtained. We have another sample table. So this is the table 15.2 entitled Frequency Distribution of Patients' Anxiety Scores. So the 60 anxiety scores are presented as a frequency distribution, and this arrangement makes it convenient to see the highest and lowest scores. So the most common score were the scores clustered and how many patients were in the sample. So the total sample size is typically designated as the letter N. As you can see from below, our total sample size, or the N, is a total of 60. So none of this was easily discernible before the data were organized. So some researchers display frequency data graphically in a frequency polygon, same as figure 15.1. In such graphs, scores typically are on the horizontal line with the lowest value on the left, and frequency counts on percentages are on the vertical line. So data distributions can be described by their shapes. For this, whereas you look for our figures, this is figure 15.2, example of a symmetric distribution. So when we talk symmetric distribution, if it occurs, so there will be folded over. So the two halves of a frequency polygon would be superimposed. Now, for this sample, we focus on the letter A, the positive skew. In an asymmetric or skewed distribution, the peak is off-centered and one tail is longer than the other. So when the longer tail is pointed toward the right, the distribution has a positive skew, as in the first graph of the figure 15.3, the color red. So personal income is an example of a positively skewed attribute. On the other hand, if the longer tail points to the left, the distribution has a negative skew, as in the second graph in figure 15.3, the color blue one. Age at death is an example of a negatively skewed attribute. Here, most people are at the far right end of the distribution, with relatively few people dying at an early age. How you state or how you write your data or how you interpret the data is very important, very crucial. We really have to observe proper way of describing the graphs if so happen that you use observing the positive and the negative skew of your study. So you really have to follow this sample. Now, another aspect of distributions shape concern how many peaks or high points it has. So we have a unimodal distribution has one peak, as you can see from graph A of our figure 15.2, whereas a multimodal distribution has two or more peaks, as you can see from graph B. So two or more values of high frequency. A multimodal distribution with two peaks is a bimodal distribution, as illustrated in our graph B of our figure 15.2. So furthermore, a distribution of particular interest is the normal distribution, so sometimes called as the bell-shaped curve. A normal distribution is symmetric, unimodal, and not very peak, as illustrated in our graph A again. So many human attributes, like for example your height, intelligence, approximate a normal distribution because of course our height increases and even our intelligence. Now let's proceed with the central tendency. So frequency distributions are a good way to organize data and even clarify patterns. It can really help. But often a pattern is less useful than an overall summary. So our researchers usually ask such question as, what is the average oxygen consumption of a myocardial infarction patient during pathing? Or may also ask, what is the average weight loss of patients with cancer? So such questions seek a single number that best represents a distribution of values, because an index of the typicalness is more likely to come from the center of a distribution than from a extreme, such as indexes are called measures of central tendency. So lay people use the term average to refer to central tendency. So they have the same meaning. But in research, of course, we use the term central tendency, not average. But researchers avoid this term because there are three indexes of central tendency. We have the mode, the median, and the mean. So it really depends on the tools you use, and of course, it really depends to what type of study you conducted. So when we talk about mode, the mode is the number that occurs most frequently in a distribution. In the following distribution, the mode is 53 from our example. We have 1, 2, 3, 4. So our mode is obviously number 53. So the value of 53 occurred 4 times, a higher frequency than for other numbers. So the mode of the patient's anxiety scores in table 15.2 earlier was 24. If you try to go back with our first samples. So the mode, in other words, identifies the most popular value. The mode is used most often to describe typical or high frequency values for nominal measures. So this will fall under nominal measures. For median, the median is the point in a distribution that divides scores in half. Consider the following set of values. We have that 1, 2, 2, 3, 3, 4, 5, 6, 7, 8, 9. So the value that divides the cases in halves is midway between 4 and 5. And thus, 4.5 is the median for the patient anxiety scores. So the median is 24, the same as the mode. So an important characteristics of the median is that it does not take into account individual values and is thus insensitive. Take note, insensitive to extremes. So in the above set of numbers, if the value of 9 were changed to 99, the median would remain 4.5 because of this property. So the median is the preferred index of central tendency to describe a highly skewed distribution. In research reports, the median may be abbreviated as letter M and letter D. So capital M, small letter D, or MDN, capital M, small letter D, and letter N. And lastly, under our central tendency, we have your mean. So when we talk about mean, this is equal to the sum of all values divided by the number of the participants. So what people refer to as the average. So the mean of the patient's anxiety scores is 23.4 because it has a total of 1,405. So you divide it with your 60 total number of respondents. So as another example, here are the weights of your 8 people. We have 85, 109, 120, 135, 158, 177, 181, and 195. So in this example, the mean is 145. Unlike the median, the mean is affected by the value of every score. So if we were to exchange the 195 pounds person for one weighing with 275 pounds, the mean weight would increase from 145 to 155. So this is not insensitive. This time, your mean is very sensitive. Now let's review your variability. So two distributions with identical means could differ markedly with respect to shape. Like for example, how skewed they are and how spread out the data are. For example, again, how different people are from one another on an attribute. So this section describes the variability of distributions. Consider the two distributions in Figure 15.4, which represent hypothetical scores for students from two schools on an IQ test. So both distributions have a mean of 100, but the patterns are really different. So School A has a wide range of scores, with some below 70 and some above 130. While for School B, by contrast, there are few low or high scores. So School A is more heterogeneous or more variable than School B. And School B is more homogeneous than School A. So our researchers compute an index of variability to express the extent to which scores in a distribution differ from one another. The most common indexes are the range and standard deviation. First, we have range. The range is the highest score minus the lowest score in a distribution. Take note, you subtract it from the highest score to the lowest score of the distribution that you have. In the example of patients' anxiety scores, the range is 15. Since 30 is the highest, 15 is the lowest, so you subtract, that's 15. In the distribution in Figure 15.4, the range for School A is about 80, since your highest is 140 and the lowest is 60. So you will get 80. Whereas the range of School B is about 50. Highest 125, you subtract from lowest 75. So the chief virtue of the range is its ease of computation because it is based on only two scores, no? You have your highest and the lowest score. However, the range is unstable. From sample to sample from the same population, the range tends to fluctuate considerably. So moreover, the range ignores score variations between if there are two extremes. So somehow it's really unstable. Now for standard deviation. So the most widely used variability index in the standard deviation. Even me, in my studies, I've been using standard deviations. So like the mean, the standard deviation is calculated based on every value in a distribution. So the standard deviation summarizes the average amount of division of values from the mean. In the anxiety scale example, the standard deviation is we have 3.725. In research reports, the standard deviation is often abbreviated as small letter s or capital S and letter D. Now, a standard deviation is more difficult to interpret than the range. For the standard deviation of the anxiety scores, you might ask 3.725 what? So what does the number mean? So we can answer these questions from several angles. First, the standard deviation or SD is an index of how variable scores in a distribution are. And so if, for example, male and female nursing students had means of 23 on the anxiety scale, but their SDs were 7 and 3. So respectively, we would immediately know that the females were more homogeneous. So we have an example. So this is figure 15.5, the standard deviation in a normal distribution. So the standard deviation represents the average of divisions from the mean. So the mean tells us the single best point for summarizing an entire distribution, and a standard deviation tells us how much, on average, the scores deviate from that mean. In the anxiety scale example, they deviated by an average of just under 4 points. A standard deviation might thus be interpreted as an indication of our degree of error when we use a mean to describe an entire sample. In normal and near normal distributions, there are roughly three standard deviations above and below the mean. Suppose we had a normal distribution with a mean of 50 and an SD of 10, as you can see from our sample, figure 15.5. In such a distribution, a fixed percentage of cases fall within certain distances from the mean. So of all cases, 68% fall within one standard deviation above and below the mean. Thus, in this example, nearly 7 of 10 scores are between 40 and 60. So in a normal distribution, which is you got 95% of the scores fall within two standard deviations from the mean. So only a handful of cases, about 2% at each extreme, lie more than two standard deviations from the mean. So using this figure, we can see that a person with a score of 70 achieved a higher score than about 98% of the sample. So this is table 15.3. So example of a descriptive statistics selected by psychosocial risk and resources for low-income women. So it provides the ranges and even the mean, and enclosing with parentheses the standard deviation of every mean. So far, our discussion has focused on univariate or one variable, so of descriptive statistics. So the mean, mode, and standard deviation describe one variable at a time. While for bivariate or two variables, descriptive statistics describe relationships between two variables. So we are now reviewing the bivariate descriptive statistics. So let's have first the crosstab or the contingency table. So it's a two-dimensional frequency distribution in which the frequencies of two variables are cross-tabulated. So suppose we had data on patient sex and whether they were non-smokers or light smokers. So when we talk light smokers, less than one pack of cigarettes a day, while for heavy smokers, it's more or less one pack a day. So now, the question is whether there is a tendency for men to smoke more heavily than women or vice versa. So whether there is a relationship between smoking and sex. So usually we observe this in our studies. We try to compare if there is really a relationship between the gender or the behavior or the culture. So fictitious data on these two variables are shown in our next sample table. So we have this sample table, 15.4. So 6 cells are created by placing one variable, like for example, we have sex as one variable, so along one dimension, and the other variable, which is the smoking status, along the other dimension. So after subjects' data are allocated to the appropriate cells, percentages are computed. So the crosstab allows us to see at a glance that in this sample, women were more likely than men to be non-smoker, which has a total of 45.4% versus 27.3%, and less likely to be heavy smokers, which has an 18.2% versus 36.4%. So most likely this is how you write your interpretation of data or the results of the data gathered from your respective research studies being conducted right now. So contingency tables usually are used with nominal data or ordinal data that have few ranks. So in the present example, the sex is nominal, of course, and smoking status as defined is under ordinal. Now, let's proceed with correlation. So, relationships between two variables are usually described through correlation procedures. So, the correlation question is, to what extent are two variables related to each other? For example, to what degree are anxiety test scores and blood pressure measures related? So, this question can be answered quantitatively by calculating a correlation coefficient, which describes the intensity and the direction of a relationship. So, two variables that are related are height and weight. So, tall people tend to weigh more than short people. The relationship between height and weight would be a perfect relationship if the tallest person in a population was the heaviest. So, the second tallest person was the second heaviest, and so on. The correlation coefficient summarizes how perfect a relationship is. So the possible values for a correlation coefficient ranges from in negative 1 point through zero point 0 to positive 1.0 if height and weight were perfectly correlated. If only. So the correlation coefficient expressing this would be 1.0. So the actual correlation coefficient is in the vicinity of 0.5 to 0.6 for a general population. So height and weight have a really positive relationship because greater height tends to be associated with greater weight. But when two variables are unrelated, the correlation coefficient is obviously zero. So one might anticipate that women's shoe size is unrelated to their intelligence. So women with large feet are as likely to perform well on IQ tests as those with small feet. So the correlation coefficient summarizing such a relationship would presumably be in the vicinity of 0.00. So the most commonly used correlation index is the product moment correlation coefficient, also referred to as the Pearson's R, so which is computed with interval or ratio measures. It is difficult to offer guidelines on what should be interpreted as strong or weak relationships because it depends on the variables of your study. So, if we were to measure patients' body temperature both orally and rectally, a correlation, which stands for letter R, of 0.70 between the two measurements would be low. So for most psychosocial variables, example, you have your stress and severity of illness, however, an R of 0.70 would be rather high. So perfect correlation should be positive 1.0 and negative 1.0, where are extremely rare. So in research reports, correlation coefficients are often reported in tables, displaying a two-dimensional correlation matrix. So you can observe that one as you gather your data, as you interpret your data on your chapter 4. So in which variables are displayed in both rows and columns. To read a correlation matrix, one finds the row for one variable and reads across until the row intersects with the column for another variable as described in the following samples. So this will be discussed further by our respective research advisors. So they will be providing samples so that you can appreciate more the relationship, how they correlate from each other, two variables. Now, as we end the first part of my discussion or for our review for today, we have describing the risk. So the EBP or evidence-based practice movement has made clinical decision making based on research findings an important issue. So there are a number of descriptive statistical indexes that can be used to interpret findings and facilitate such decision making. So many of these indexes involve calculating changes in risk. For example, a change in risk after exposure to a potentially beneficial intervention. So the indexes described in this section are often not reported in nursing research articles, but they are routinely described in books on ABP or evidence-based practice. In this section, we focus on describing the dichotomous outcomes. For example, had a fall or did not have a fall in relation to exposure or non-exposure to a beneficial treatment or protective factors. So that finally ends the first part of our review for today. So thank you for listening and see you on the second part of our discussion.